So we talked about these transmissions, but of course our end goal is to come up with equations that describe the kinematic relationships that result from those transmissions. So in this class, the key kinematic relationship is that for a circle, and it's as follows. It's the arc length, which in general we can just call S, but we'll use different variable names for it, which is a translational motion or position, and the radius of the circle about which is being rotated, and then also the angle. And it's really important when you use this equation that this theta, this angle, has to be in radians. And so if it's given an angle in degrees, or you need to solve for it in degrees, just remember this relationship, that pi radians is 180 degrees, and then you can easily change the units to whatever you need to have. So let's just take a quick look at this circle down here, just as an example. Here's the radius r of this circle, and if this this vector here rotates by an angle theta, so now that vector winds up here, the tip of it has traveled by an arc length that is of the value s. And r and s can be in any units you want, really, as long as they're the same in this equation, because radians is really sort of a unitless parameter. So if you have r in millimeters and you multiply that by theta in radians, then s, the arc length traveled, will also be in millimeters. So let's look at how this kinematic relationship is useful in a haptic device or another kind of mechanism. Let's illustrate the utility of this kinematic relationship with an example. And like the belt and pulley example that we saw earlier, we have two pulleys here. Each one is pinned. So this one is pinned at the center here, and this one is pinned over here. And each one is free to rotate, and the belt attaches the two of them. And the belt's not stretchy, so this is a 1 degree of freedom system. The red dot there is just there to identify a point on the belt so you can see how that moves. So let's see what happens as, let's say, theta 1 is the driving pulley and theta 2 and the belt will follow. So theta 1 begins to rotate and everything else moves. We'll just rotate a little bit more and the belt reaches the surface. The point on the belt reaches the surface of the first pulley and starts to travel over it. So there's an example of the physical movement. Now let's look at the equations that can be used to describe the relationship between theta 1 and theta 2. So the first thing that we recognized is that the arc length of a point on the belt as it travels over the first pulley is going to be r1 times theta 1. Similarly, the arc length that would be traveled over the second pulley would be r2 times theta 2. But because the belt is just one belt and it's not stretchy, S1 has to equal S2. So if we defined a point x, any point x on that belt, the amount of distance that it travels, x, has to equal the arc length the belt travels over the first pulley as well as the arc length traveled over the second pulley. So now we have a relationship where we just have to set these two quantities equal to each other. And when you do that calculation, you get theta 2 as a function of theta 1. And we can do a reality check to see if this is correct. So we know that r1 is larger than r2. So that means that theta 2 should have rotated more than theta 1 because of this ratio, r1 over r2, because this is going to be larger than 1, because r1 is greater than r2. And indeed, we saw that theta 2 rotated a further distance.